All right, what is up, everyone? Welcome to week 76, Chill Kernel Hacking for Fun. Thanks for joining. Quick recap as usual. So we're now in the era of streaming where I'm kind of doing whatever I want. And these days it's kind of like C++ stuff and whatever. And what I had in mind for today is porting to Clang, because there's a lot of good reasons why we might want to do that. Yeah, just gonna get my chat widgets and whatever set up quickly. But yeah, there's a lot of good reasons to use Clang instead of GCC, especially if we're going to be getting into a bit more C++ stuff with the OS. The one really concrete reason is because GCC doesn't support non-trivial designated initializers for C++, but Clang does as a language extension. And it turns out the OS uses a lot of these. Let me just show you. We've kind of gone through this in previous streams. I'm just gonna clear out. A good example of this would be entry page dir. I'm talking about stuff like this, console.c. Console.c here. I'm talking about stuff like this also. And the C code base of JOS relies heavily on that. And then trying to compile this with a C++ compiler doesn't work because GCC doesn't support this, and for some reason. But Clang actually does as a non-standard language extension. So I don't know the details there. I don't know why it's not supported in C++, but what I do know is that, let me see if I have my compiler explorer thing open. If you try to, okay, here is a basic example. And this fails to compile with GCC x86 64. We have a global array, and we're just trying to initialize some selective members. If we switch this to x86 64 Clang trunk, it actually does compile. It does give you a warning saying something about this being a C99 extension, but at least it does compile. So that is just one kind of concrete reason to actually switch over to Clang. All right, welcome to everyone joining the chat. Yeah. Waiting to see if the chat widget works today. But okay, yeah, so basically that's the kind of the topic for today. I would like to use Clang. Let's just get started with that. Don't really need this right now. Okay, as you can see, I was doing a little bit of just trying to experiment with Clang. I've been told that it should be pretty easy to switch to Clang, but let's just I just want to make sure I'm in a clean building state and I'm not, for probably a kind of dumb reason. Something is just like not. Something to do with this. I changed this last minute. I do def. Undefined reference to operator delete. That's kind of interesting. It's yeah, we don't have an operator delete. Honestly, this problem is not really that important. I think I ran into this because last time I had a weird mistake and I didn't declare the destructor virtual or something like this, but I think things actually do compile. So yeah, that's like not really the important part. So temp fix, that's not really the important part of what we're trying to do today. So I guess if we're trying to port to Clang, then what would make sense as a good starting point? I guess maybe even checking back out to a version of the code base that doesn't have any C++ stuff, just to make it a bit more clean, and introduce less concepts. So just a direct port of the C code base and just compile that with Clang instead of GCC. Okay, so yeah, guess let's try to do that. So I need to find out a place to check out to. I guess probably this commit. This is where we sort of start messing around with C++ stuff. So I'm just going to come back here, check this out, and make a new branch. I'll call it Clang. And we'll just make clean and make, and just make sure we're at a clean starting place. Things run, things boot. This is all expected. So that's good. I mean, we do have this panic in there. We've had this kind of for a while now, because for a long time I was just playing with some of these boot protocols and stuff, and I wasn't interested in booting the entire OS. So for that reason, we did have the panic very early on. I wonder if things still work. Yes. Okay, so here's like the full OS, and it did fully boot, and it's actually running well. So that's cool. So that's actually probably a good disable early panic. Okay. So I guess kind of like a first step here is I need to figure out how to get a cross compiler, how to get Clang with the necessary cross compiler. I've already brew installed LLVM as a guess about how to do this, but maybe I will just come here, make a work area for today. It is 13th of July. Clang. Okay, so how... Yeah. How to cross compile with Clang. I think this is pretty easy. It's like a target. You pass like dash arch or dash target or something like this. So I'm just going to immediately whip out Copilot. And just ask some basic questions. I would like to port my OS to compile using Clang instead of GCC. I'm on a Mac, but cross-compiling the OS to run on 32-bit x86. Currently, I'm using an i386 ELF GCC toolchain from Homebrew. I've done brew install LLVM to try to get a Clang. First basic question, what command line and arguments do you pass to Clang to cross compile? How might I test if my Clang support has a i386? Wait, yeah, I don't know. I need a Clang with a 32-bit x86 backend. I sort of doubt that brew install LVM will get me that. Okay, so maybe my question is, oh wait, there's way too much stuff here. Oh, what? Where did my prompt go? I pressed the up key or something, and then okay. How do I install Clang as a i386 ELF cross compiler to build my OS when I'm on a Mac? Don't generate code. What's up, Zabriel? Good morning. Okay, time to also update the stream text. We are doing port to Clang. What did it say? How do I get rid of... Yes. Wait, does it keep? How do I get rid of these things? I just want to make this a bit smaller. Did that change my working tree? Yeah, that did a bunch of stuff. Okay. Okay. Where? Use Homebrew with a custom tap. Maybe I will just also... What? This is an interesting suggestion. It's saying use Clang as the compiler only, but continue to use the GNU linker and assembler. Yeah, we could build Clang from source. It's not that hard. I sort of want to avoid doing that if I can help it though. This looks interesting. What? i386 muzzle cross. Let's do a bit of research about what this is. Also, maybe just a quick actual search. OS dev clang cross compiler 32-bit x86 i386. Surely someone has talked about this before. I'm going to add a document. Let's take some notes. Okay. Clang. Can I OS dev from Mac OS? Maybe that's interesting. Cross compilation using Clang. Okay, nothing too interesting came up. Oops. Okay, just collecting some links. LVM cross compiler. That sounds interesting. Okay, does anyone talk about Clang here? People are talking about GCC. Someone wrote a blog post. Someone has a GitHub project. Okay. Clang? Okay, interesting. CCC host. This is very old though, so I'm a little bit wary, but actually this is kind of an interesting sort of this image got kind of big. Yeah, that is sort of interesting. Yeah, it would be great to use Clang for or rather use the LLVM toolchain for everything. But maybe it is easier to just try to get it, just to try to start with Clang being only the compiler. Okay, this is some random operating system from someone, and I don't see the word clang. In fact, I see quite a bit of GCC, so not really loving the Xcode proj. Wow, that's interesting. Also, let's make sure to get this thing going. It's actually probably time for a quick 20-second break to stand up and stretch. Let's just do that right now. Okay. Okay, so I don't know, this is like kind of random. So here are some docs. So let's just see what. Okay, this is actually pretty useful. We will... Yeah, we're going to need something like this. i386 PC elf, something like this. All right, this link is good. This link does not seem that good. This link seems interesting. So I have a couple clangs on my system. I have the normal user bin clang, which I guess is installed with Xcode or something like this. And I would guess that this does not have the support I need. Like, why would they ship support in their clang for compiling 32-bit? And I need to find out a way to test this. So maybe I can just vim main.c. I just need to make a basic like function, or like basic C file, I guess. Maybe I can, like, it doesn't really need to do very much. And arg, return arg, you know, this is like a pretty simple C function that doesn't have any dependencies and just does some stuff. And I wonder if I could then try to compile something. So if I do clang target i386 PC elf c main.c o obj.o, that is very interesting. That actually seemed to work, which I completely did not expect. What? Why did that work? So file object o, holy crap. I'm just gonna screenshot that. That's pretty cool. So that that even is using like this default clang, just to really make sure. What happens if I... Okay, that's kind of weird. I tried to make the target invalid and it did not give an error. Let me just delete. Oh, let's try that one more time. We still have obj.o. So It's kind of peculiar. What happens if we really mess up the last part? It still kind of works. That's very weird. Are you kidding me? Does it really if you do this like weird EX thing, does it interpret that? It somehow interprets that as elf. What if I do AAA? Am I going? That's so. That's like very strange. It seems like if it doesn't know, it just defaults to elf, possibly. Right? We are deleting object.o. It reappears and it's an elf. That's crazy. Does that seem kind of crazy to anyone else? I am extremely surprised that, almost to the point where it feels like I'm doing something wrong, that this thing like sort of doesn't matter. It seems so. Like, what if I yo, Ismail, what up? Nice to see you. How are you doing? I am trying to figure out why Clang is acting extremely strangely. So, turns out you can pass like garbage as the last part of the target triple. You know what, I'm just going to do a watch command that's like file obj.o. Yeah, we're taking a look at switching to Clang. That's exactly right. So if I remove obj.o, right, but this thing's gonna fail. What happens if I arch? Let's try like arch apple Darwin, or arm apple Darwin, for example. So it produces, yeah, okay, so that like is interesting. It produced a Mach O, I don't know, something. So that's kind of interesting. Yo, what's up, Lizard? Nice to see you. We're just playing around with Clang. Did you know that if, oh wait, I should keep this going, but I'll make it update a bit faster, maybe 0.5. So did you know that if you pass like junk to the last part of this thing, it produces an elf anyway, even if it can't parse the last part? That's like pretty. What if it's Darwin? It produces a Mach O. Interesting. It seems to fall back to elf if it cannot parse the last thing, which is very interesting. So I'm learning a lot right now. I'm learning that, so number one, my default like Clang on my Mac actually has a cross compiler built into it. It's capable of generating i386 code without any additional configuration, which is like very cool. Also, I don't completely understand why, but maybe it makes sense if you imagine actually, I have no idea. The Clang that comes with the system is supposed to be the system toolchain, and it's meant to target the system I'm running on, which is an ARM Mac. So, yeah, like it's supposed to target my native system, and it would be extremely unusual to build x86 code to run on the Mac, but maybe there's a reason to do this. I don't know. That's pretty interesting. Yeah, okay. So it turns out I didn't need to brew, and like I brew installed LLVM because I thought that would be useful, but maybe it's not. Okay, let's just what happens if I do this? i386 Apple Darwin? Wait, no, that it was already a Darwin. Okay, so PC. I mean, honestly, this doesn't really matter. Like I've already tested the main thing I was interested in, which is the fact that actually I can produce yeah, like 32-bit x86 object files very easily, apparently. Maybe. So I guess that's a good starting point. And I don't know. I guess we could just try to use that in the build system instead of GCC. It almost seems a little bit too easy, but I mean, it probably something is going to break, but where am I looking? I'm here. So what are we doing? So CC, instead of doing this, we're going to do this, I guess. Something along these lines. And so this is like how I'm swapping out the compiler, because the rest of the build system just uses this CC variable to reference the compiler. So this is probably going to blow up in a massive way, but let's watch that happen. So I'm going to, I don't know, I'm just going to make clean. Interesting. So I already had a problem with cleaning. No tree ch. So yeah, so who knows what that means. Why clean? Yeah, this is pretty confusing. Why is clang getting invoked? It's maybe because there's this phony, but clean is marked as a phony rule. I don't even really get the phony stuff, but completely not obvious to me why clang just got invoked. But let's just run make and see what happens. Okay, so that's probably to be expected. Clang doesn't know about this parameter we were passing to GCC, which, to be honest, sounds extremely exotic. So I'm just going to comment that out. Let's try one more time. What's up, Ragil? Nice to see you. Phony forces a rule to be executed regardless of its dependencies. I guess, to be honest, I legitimately don't know. I never really took the time to learn make files that well. So, but that sounds about right to me. Yeah. Okay, so we are off to the races. kind of, and we're passing clang into a bunch of these things. And now we're getting some errors. Expected expression. init.c. Okay, I think this I think this is because I'm missing braces. Wow, that was a weird way of doing it. Yeah, I don't know the rules around this stuff too well, but it's interesting that GCC allowed not having braces, but Clang seems to have a problem with that. But whatever, I guess that fixed it. Okay, now we have a problem with m.c. So maybe just before diving right into this, so this is interesting. So it wasn't actually that hard to test whether the Clang works and can cross-compile. And it also wasn't that hard to just swap it out into the build system to try to use it. And in theory, swapping out compilers should be like a completely seamless thing if your C code uses standard C. But in practice, it's not that easy, and we run into little things we need to patch up to make it work. And that's what we're seeing right now. Switch condition has a Boolean value. Okay, yeah, so this is in the implementation of static assert. And apparently this is some kind of hack you can use in C to get static asserts, which for the longest time weren't in C. I think only very recently have you been able to static assert in C, like C11. I mean, which is like over 10 years old, but or C23 even. But before that, if you want to have a static assert, you need to like do a weird hack. Okay, and apparently it's like a pretty brittle hack or whatever. What do I do? Switch condition has a Boolean value. So switch bool. I'm just like kind of curious about this warning. W switch bool. Wow. C bool. Do not warn when a switch statement has an index of Boolean type. Suppress this warning by casting the controlling expression to a type other than bool. I'm going to stash this in our notes for today. And maybe, I'm not like really totally getting this, but what if we cast something to an int? Does that help? No, that did not help. Which condition has a Boolean value? I mean, worst case, index has an index of Boolean type. Okay, I don't know. It's not really that important to get stuck on this right now. I'm just going to drop this. I think a simpler hack is just to disable that warning. So I'm just going to add something like this. I'm going to add a no switch bool. And we're just kind of manually going to hard force that error, that warning to not appear, which means that error should go away. Okay. I mean, it might still be kind of good to check that static asserts still work. So if I just do the opposite, if I do equals 0, this should fail. And it sort of already seems like it is failing, but I'm just going to try to compile things anyway. Oh, is that how that works? Is it already time for a 20-second thing? All right, be right back. Okay, that's actually interesting. I actually don't really know. Yeah, stretch. I actually don't really know if I've seen the static assert fail before. But so first off, the build failed. Second of all, the warning is like extremely not obvious that the static assert is failing, but this is the error you see. And I guess the way this static assert hack works is if this condition is false, it evaluates to 0, it's going to produce case 0 here, which is going to be invalid because there's already a case 0, and that is a syntax error or something like this, or whatever, and then so the build will fail. So I think so that we are observing that static asserts do still work, and that is actually how they've always worked. And so this thing is going, but this thing evaluates to true, and so it generates like a 1 here, and it's valid or something. Okay, moving on. Wow, now we're going into lightweight IP, which I don't really want to modify too much. Self-assign. And yeah, I think that's just to suppress any warnings about arg not being used. What do we do? Just comment this out. Interesting. All right. Is there? Yeah, that would be another option too. I'm sort of thinking I don't really want to modify the source of lightweight IP, to be honest. It's not really code I control, and it's sort of conceptually separate to the project. And I would rather work around this with some more of this kind of thing and just document that its purpose. Okay. No self-assign. Okay. These suppress warnings in lib when compiling with clang. So yeah, so basically I've removed that comment out here, and we should still get this same error, and we can quickly peek at what this is all about. .c. Okay, so we have this big list type of thing. Wait a sec. This is actually really okay, yeah, no. So this is just another use of that very common pattern that we're seeing in JOS, but also in lightweight IP, where we have this static array that is populated at compile time at specific specific array elements are populated at compile time. And there's a problem: initializer overrides prior initialization of this sub-object. Okay, so the one on 47 conflicts with 17. And that's because these E woodblock and E again are the same value. And so now it's warning us that we are overriding actually this. So this line is actually technically not used at all, which is kind of an interesting, like, legitimate warning. So yeah, what's up, useless? Yeah, we're working on trying out clang, taking clang for a spin. So I'm just going to do this. Yeah, okay. And now we should just be able to, oh wait, I need a no here. Okay, now this is interesting. So we actually were able to like compile pretty much everything, I think. And now we're just running into a problem with like linking and libgcc. I'm just gonna get a quick sip. All right, so what's the deal with libgcc anyway? So like GCC is your compiler, and it takes your C code and converts it into assembly. And like usually most of the time, it can just directly transform the code just directly into assembly that just like runs inline in the function. But from what I understand, there are occasionally times where GCC does not, for various reasons, it does not generate the assembly inline in your functions, but rather it will actually emit a function call out to a helper library that's loaded into the program, and it actually generates a function call rather than just like normal assembly stuff. And these helper functions live in libgcc.a. They're kind of like compiler support, like runtime support routines, and that's like my understanding of that. And apparently you need to like link it in. Okay, yeah, so Lizard, yeah, so you had an example with this actually. So in your case, your hardware didn't have multiplies, and so libgcc can emulate this in software or something like this. Exactly. Yo, what's up, Digitalized? Nice to see you too. We're hard at work, working on some clang stuff. And so what's up with libgcc? So libgcc, oops. Libgcc. So, right, so previously we were using GCC as the compiler. It got loaded, like GCC is in this CC thing, and you can, like GCC can print out a path to where its libgcc lives or something like this. And then we were using this and like used this somewhere. Like for example, in our build step to link the kernel, we would have all our kernel object files, but then we would also include the GCC lib thing in that big list. And that's kind of an interesting question of what do we actually do here. I mean, there's a couple options. One, we could just try to replicate the libgcc thing with clang, try to find the equivalent command line arg or whatever. But the problem is I would be kind of surprised if there was like a libclang for i386, but like on my system to use, but that's worth at least asking AI or whatever what the equivalent of this, what is the equivalent of blah 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 for clang. That's a GCC flag. What? What? But wait, it didn't cannot find, wait, I'm super confused. So libgcc.a, somehow that appeared there. Okay, no, this, we are building the user programs right now. We're building a building user space. So is it user make frag? Okay, so, and here is where we see how that command line is constructed. And that's why this gcc lib thing is at the end. But that actually means that clang, it printed something out. So if I copy this, that's kind of weird. What happens if i386 elf gcc? Yeah, so this is how things were working previously. That's actually kind of hilarious that it just prints libgcc.a as if that means anything. That's actually hilarious. Okay, so technically, yes, it does support the flag. It doesn't actually do anything meaningful with it. Like GCC actually gives you a path to like a real libgcc you can use. All Clang does is print out the text libgcc.a, and so that's it's not very helpful. Okay, but maybe, I mean, there's two other main options here. I actually kind of wonder really if the libgcc thing is necessary. Yeah. Also, Insta Headshot, what's up? Do you have anything special going on in VS Code and Vim? Let's see. I have a custom Vim RC with just some custom keybinds, and I use some Vim plugins, camel case motion. Yeah, Vim Sneak is really cool. Vim Surround. Yeah, that's pretty much it. Just also, and Vim scroll. No, it's just like the VS Code scroll, smooth scroll. Yeah, smooth scrolling. I found out about that recently. It's pretty helpful. So what I'm just thinking is like, what if we just don't have this? Like, what if it's an empty variable, or like I don't even know, an empty string? Is that how you do an empty string? I think, or just like this. What if we just totally don't? Okay, and here's the answer. If we just totally don't have the libgcc, then here's the problem we run into later, where GCC is emitting all of these function calls to its internal runtime library, and it's assuming that its internal runtime library will be available at some point later to like link this. In practice, we're not providing that runtime library, and so there are linker errors. So let's check out this thing then. I mean, there's a bunch of different solutions here. We could also continue to use GCC's runtime library, actually, maybe. I wonder if that would work. I think I'm just going to sketch out a bit of like a path. So we start out with GCC only, and at the end destination is going to be something like clang LLVM toolchain only, and it's kind of a big step to go directly from here to here, but maybe there are some intermediate steps we can use, like clang compiler, but GCC libgcc.a. And so that's like a little bit weird because we're like using both tool chains, but as an intermediate step, maybe it's useful. Something else that we're doing right now is clang compiler, but GNU linker and assembler. because I haven't changed any of that part right now. Like I'm still just using a GCC prefix AS, AR, LD. And so we're like a bit in this sort of like halfway world between the GCC and also Clang. But it's just kind of an incremental approach. And so, yeah, we're kind of in the middle, and we can imagine ourselves eventually porting over. So let's just, yeah, Wizard, let's just try that idea of, what if I just call this, I mean, like GCC? Is that going to cause problems? Is capital G GCC used anywhere? Not as far as I can see. So, so that means we can then just like take this, but then we just change it to GCC. And now we're going to be like halfway using each. And that worked. We can see that we were able to link some of these user programs now, which is kind of cool. Yeah, what do you want to accomplish by doing kernel hacking in C? Yeah, the idea is just to learn, and eventually it would be cool to make my own operating system. And what I'm just doing is I'm working on the building blocks, or kind of prerequisites to get there. Because with my own operating system, I think I would probably want to use Clang. I would probably want to have C++ support. I would probably want to use the LeanMine bootloader or whatever. And these are all things we've been working on in the past couple of months. And so basically I just see myself as right now just knocking out some prerequisite building blocks. And apparently it's already time for another 20 seconds, so feel free to join me for a quick stretch. All right, so moving on. So now we're back into the world of compiler errors, but maybe I will just do a quick, maybe I'll just, I haven't been committing as I go, so maybe I will just do that. So first thing would be this, switching that out. Yep, so we're going to use Clang instead of GCC. And then now we are fixing various compiler problems. I might just do that all in one commit later. And then just this thing was yeah. Use GCC's lib GCC as an intermediate step. Eventually, we want to use Clang's lib Clang instead of this. Okay, so now we have yeah, okay, whatever. So back over here, test BSS. Array index is past the end of the array. It's kind of interesting that Clang is giving us different and more warnings than GCC was, because this code compiled cleanly without warnings on GCC. But And I thought that version of GCC was pretty new, but maybe there are just differences in the defaults, and Clang activates more warnings by default or something like this. Let's just take a look at testbss.c. So we have this like big array. Oh, interesting. Okay, good. Now doing a while to write off the end. So this is intentional. So what do we do about this? I mean, that's actually a good warning to have. And so it's not amazing to disable it. So what we can do maybe is just like simulate this with some pointer math or something like this. So rather than doing big array blah 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 blah, we do big array char star, okay, big array char star plus 4 times array size plus 1024 or something whack like this. I think I got that math right. I mean, so this is an array of uint 32t, so each are 4 bytes, and so therefore when you pass an index in, it's that times 4 is the actual memory location, and I just tried to simulate this like so, and it's writing 0. So yeah. All right, so I think that sort of bypassed the warning. Yeah, I mean, I could have disabled the warning for this file. I don't know. That sounds, I don't really know how to do that. So, so yeah, I don't really know if Clang is able to. Clang can't really see past this expression because we're casting away big array into something else, and it, yeah, I think, yeah. Okay, next up, in direction of non-volatile, null point will be deleted, not trap, fault, read. We're running into all sorts of these warnings because all of these user programs are doing extremely weird and like slightly like malicious stuff. And yeah, okay, will be deleted, not trap. Null dereference. Will be deleted. Or qualifying pointer with volatile. I think volatile? Okay. So if you make it volatile, apparently then you're allowed to dereference null pointers and yeah, or whatever. Fault no stack.c. Tile fault bad handler.c volatile fault evil handler.c volatile. Okay. Wow, got 20 people in the chat. That's pretty cool. All right, what is going on? So yeah, I would agree. I think Clang is a little bit more rigorous than GCC. At least that is kind of what we're seeing with these issues. D.C. I mean, I'm going through the effort of fixing these, but the reason these are failing the build is because we have W error on. I mean, a really easy way to just like get it working is to disable W error, but I was just hoping we could keep it on. It's kind of, I don't know, a nice practice to avoid, like if you have it on, then it's not, then you can't just let all these like warnings pile up and stuff, and so it's a little bit of a nice like just rigor thing. FD is used uninitialized whenever if condition is true. What? Yeah, that's actually true. That's a legitimate bug. Wow, yeah, that's a legitimate bug. FD is uninitialized here. It does not get initialized until here, but we do some error checking and we go to error and actually use it. So that's kind of bad. What's R? Yeah, it's a legit bug. I think what we need to do, well, first of all, maybe R should actually be initialized or something. I don't know. I sort of don't remember. But R is a return code. And blah, 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 blah. I think what we need to do is kind of swap things out a little bit. So it needs to kind of be more like this. So yeah, kind of up. Go to can you debug the code line by line? Yeah, we do have debugging set up for this project, and so if necessary, we can step through the code if that's what you mean. We also can read the code line by line and find bugs. So, okay, this, I think that makes sense. The thing is, as soon as this has succeeded, we want to be using end actually, because we want any code path that fails after the open has succeeded should make sure to hit the close. But for any of the code paths that do error checking before the file has been opened, we don't need to close the file descriptor. All we do is just send an error and return out. And so I'm just gonna go to close. Let's call this close. Call that error. And I'm gonna hope that still works. All right, check it out. It built. That's cool. Yeah, check that out. We built the kernel with Clang. I'm still a little bit suspicious. I'm also just noticing these warnings here. I don't know if those are new. I don't really remember seeing it before, but I could just have not noticed. But you can clearly see we're using Clang, and this Clang thing just appears everywhere. Did you see Lemine? Yes, yes, yeah, dude. We've been using Lemine for a while now. I think that was like a month ago or something. We got Lemine working. That was week 72, so like 5 weeks ago. Checked that out. Yup. Okay, so I don't know. Let's just run it. Lemine template. Bam ho. All right. I think. Well, it's crashing. Interesting. Okay, so now we're in the lovely place where our code compiles but doesn't run. All right, I'm just going to, but it's a decent pause point, decent milestone. Clang. What are we doing here? Fix warnings. Make Clang. Make build with Clang work. Either fix warnings or suppress them. So that is interesting. I mean, so yeah, we might need to do some debugging. That's a little bit scary, but hopefully it might not be too bad. I mean, so here was our kind of branching point, this whip basic Lemine setup. And after that, we started mucking around. So just to really check, I mean, if we just check out back to here, things were working. We kind of saw that earlier. Make clean, make Kimu. Oh, okay. This is we still have the panic. I need to go to here's the commit that disables the early panic. If I check out here, if I build just to be safe, clean, build, and run, bam. So it was working. This is what it looks like when it should work. We have like a shell, and we can run some programs. We can say hello. So that means that actually something kind of interesting happened, which broke something in the OS, and now it doesn't boot. And I guess we still have a bit of time left today. So if you switch back to GCC, does it still work, or are your new changes not coming? That's actually a good idea. That's actually a great idea. What would happen if we just went, why? What if we just went here? No, what if we just went here and called this CC? So here, here, we're basically reverting the compiler change. And so we still have all this stuff that we did, like, I mean, this commit doesn't really do anything. It just changes the libgcc. We still have all this stuff, but none of this stuff was, first of all of these changes are in user programs, which don't even run in the boot process. And so none of these changes could have affected anything. So yeah, so it's actually, it's not really obvious that a code change here broke something. So I guess I would expect things to just work. It should still build with GCC, but whatever subtle detail. Oh wait, okay, I have one idea. So going back to this whole thing where we were talking about, oh, let's use Clang, but then not use libclang. Let's use Clang, but still use libgcc. Is it possible that was a stupid idea? Maybe, is it even expected to be able to go between these different things? Or is it just completely expected that kind of thing should crash? I'm slightly sketched out by that. But the good news is that if we try to debug this, we can look at the we can try to find the place where the crash happens, and we should if the crash happens somewhere in libgcc, it will hopefully be kind of obvious. So yeah, so I'm a little bit suspicious about this decision that I made, but let's check it out. Useless. What scheduler algorithm are you using? I think it's just a round robin, like the dumbest round robin you can imagine, where it just goes in a loop over everything that is runnable. Okay, so let's get ready to, I guess, time to do some debugging. So we're going to make QEMU make GDB. And where do I want to break? I guess I want to break just at the start of i386 init. All right, continue. Leave my template, enter. Oh wait, what the fuck was I doing? What? I was in the middle of trying out Ismail's idea, which was to just use GCC still, and we didn't even try that. So yeah, so basically what we observe is that actually, yeah, it's just trivially switching back to GCC works. The OS immediately works. So that is interesting. So it just shows that really it's something with the Clang, with the Clang thing. XV6 uses simple RR. Oh, interesting. I've never used RR. Yeah, I've heard a lot of things about it. I didn't actually know you could use it for operating like OS dev type of stuff actually. Okay, so anyway, so we confirmed Ismail's idea, which was a good idea, that okay, but let's double check, do things still work with the GCC? And they actually do. And so it's really something kind of interesting and exotic that happens with Clang. Oh, round robin. Oh, okay. I got you. Okay. Yeah, I was confused with RR being the debugger. Like this, it's like this cool, like time traveling reversible debugger. Okay, back to this. So let's clean it up. So now we are just back. We're back using Clang. We're gonna make, and let's try to just learn more about this crash. So we're gonna continue. Lean template, bam. And okay, here we are. So the kernel was able to boot into i386 in it. So here's the part where it's a little bit tricky to actually find out where the crash is. Like if I just press enter, it's going to reboot the machine. So maybe I could just set another breakpoint, or you know, I could just step over these functions and just kind of try to see env-init, check env-init. And that's what, okay. So that, something kind of weird happened there. Check user mem init. Yeah, so we're running into this crash now. Boot crash, kinda. But, okay, so if the crash is happening with Clang and not GCC, that pretty strongly indicates some kind of undefined behavior problem, where the code is kind of secretly relying on just like internal details about how GCC does things, like how it lays out memory or like weird stuff like that. And those are not reliable details to rely on. And Clang is probably doing something differently. And so this is interesting. So it sort of seems like we're failing in check user mem check. Let's just run that one more time. Actually, wait, can I just, can I continue? That's actually pretty cool. I actually don't need to relaunch Kemu. I can just, like, the OS reboots, and then we just catch it at the next time it hits i386 init. Okay, but what, check env init, that's a bit of a closer place. And so now we're broken at check env init, but unfortunately we're inside check env init. Can I finish and get back out? Okay. So here's what the code looks like, and check user mem check, and just to really see. So we're like, this is just a bunch of these call instructions, one right after another, because this part of the code is, that's just all it does, just calls functions. And so we're here, and if I do an N to step over, we should observe a reboot, and that's what happened. And so now we're back at the main boot screen. So something is happening in check user mem check, which is kind of an interesting place for problems to happen, because that's like sort of one of these unit testing type functions we have in the kernel, and it's not really part of the actual kernel like execution flow. It's like a weird like little side thing where we would kind of like run some like unit tests. So I mean, we could even comment that out basically. Here's what it has, and so yeah, maybe just take a moment to even see what this even does. User mem check. Okay, so this function is a set of tests for the function user mem check. And user mem check is a function that we have that we call within the kernel whenever we get pointers from user space, where user space is passing us pointers that it's asking us in the kernel to access. And we need to do some validation on those pointers because maybe user space is passing really bogus pointers or malicious pointers that point way outside of its range that it should be able to access. So we have this function, and then I guess I wrote some tests to try to just verify that various edge cases work as expected. So like accessing memory beyond the top of the user limit is not allowed, and so some tests for that. So anyway, basically what we can do is I'm just going to continue, and we're just going to catch this, and we're going to actually just break on this. I'll just take the opportunity to delete a few breakpoints that we don't need anymore. We really only need the number 4, the check user mem check. Okay, and so here we are. So now I'm just going to step through this, and at some point we are going to reboot. So .406. So we're about right here. Alignment 409. So we're making our way through. So right there, that's when it happened. So let's just get a picture of that for the crime scene. All right. So we rebooted on the call to boot map region. That's interesting. Okay, so now we're getting, so that's actually like pretty much right at the end. And yeah. Also, just want to say a quick hello to the viewers on Twitch right now. Thank you for viewing on Twitch. I'm trying to learn about how to use Twitch, and so it's super cool to have a couple viewers on Twitch. All right, boot map region. So the next obvious thing we can do is kind of narrow down our breakpoint and break exactly on that line. So now I can continue, reboot, and now we break at check user mem check. I can continue. We break immediately on the boot map region call that triggers the reboot. And we could step into, I mean, let's just maybe just before we debug, let's just try to understand, if possible, what happens here. So the idea is to map some supervisor memory below ulimit, and then try to access that memory from user space and observe that it still is not allowed, even though that kernel memory, that supervisor memory, is in the user region. User space should still not be able to access it. And this is helping protect against a bug where you could imagine the implementation of user mem check. Maybe it was kind of incomplete, and all it does is just check that the pointer is below the ulimit region, but then it didn't do any further checks about the permissions of that region. So if the implementation was flawed and all it did was check that the pointer was in the ulimit region, then this would guard against this, because in that case, the user mem check would return valid, and we want to make sure it returns invalid because we allocated it as kernel only memory. Ismail, I wrote these tests actually. Yeah, these. Yeah, I think actually I completely did this by myself, because I just wanted to have a bit of tests for, the logic in user mem check is a little bit involved. Yeah, I remember I was I even have these comments here. I was learning, I was trying to remember how bits work. And I just felt like having some tests for that. So I added them. But interestingly, and apparently, something happens with clang that makes that is not okay and for us to call boot map region. So we can take a quick 20-second break to stand up and stretch. Be right back. Okay, so anyway, we're broken, and at our breakpoint is set right at this function call. And so previously we just tried to kind of do a next to go over it. That crashes. Oh, wow. That is interesting. What happened? Wow, it rebooted on even trying to step into that function. That is wild. Yo, what's up, Sanic Toes? Yo, what kind of script are you making? I am working on an operating system. Yeah. This is interesting. Wait, so I couldn't even step into the function, actually. Let's run that one more time. Continue Lemine back here. Continue. Let's really look closely at what's going on. So we are right here. Um, holy crap, check that out. Wow, XMM. Clang is using, what is it called? A SIMD register? Wow, now that is interesting. Take a screenshot of that. So many questions. Like why, like what is up with that? So what's up with this function signature that would, okay, like we got only very normal things in this function signature. There's no exotically large structs or something like this. So that's interesting. I really don't understand what it's doing here, but let's all right, let's just step through this instruction by instruction. So we just did the sub, but what's that all about? Why? So anyway, let's just right, we're at, yeah, so who wants to bet that this is going to crash right on this instruction? I think it will, but I actually don't know. Okay, actually I have no idea what this instruction is doing. Move APS. I really don't. Okay, I guess maybe it's loading a value into the register. Maybe it's loading this value into this register, then load. I actually don't know what these instructions do, to be honest. But this is an extremely unusual function setup. Okay, so I'm gonna revise my bet. I don't think it's going to crash on this instruction. Okay, I was wrong. It did. Wow. What the fuck? That's crazy. Okay. It's loading a floating point? I don't know. Why, like, yeah. What is going on here? It would be very interesting to diff the assembly between GCC and Clang, I guess. Clang is wild in. That is absolutely true. Wait, so I'm like struggling to page back in AT&T syntax into my brain because I like always forget how this works. It goes left to right, I think. Do you have SSE enabled? Yeah, maybe. How? I think, yeah, I mean, that's a good idea. I don't know. What is up with this address? I'm like kind of curious. Is there anything 386 elf read elf, blah, 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 kernel. It's like just interesting that that address is hard-coded. I'm just kind of curious, can I, right, I can search for addresses and stuff. So if I, like, I'm just curious, what is this F0 blah, blah, blah thing? The actual solution is probably just to make sure we pass a flag to disable SSE or whatever, like SIMD mode or something like that. That is fascinating. So this like magic constant is just it's not obviously some kind of like symbol here in the kernel, although maybe it is something private. Like what? No, this is a local variable. So nothing too interesting going. It's just access. Oh wait, what? No, but that's just a pointer. So it's just passing a normal pointer. This is all super normal stuff. So I don't see any reason for exotic types to be used, but yeah, useless. I think that's the real suggestion here. What's a question I could ask just to, I'm just gonna come back one more time. So just ask blah, 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 blah. I'm just gonna copy the text. Okay, back here. Yeah, I'm gonna copy this into here. Here is code from my debugging session. It seems Clang is emitting use of the XMM0 register in the call to boot map region. Code. Can I just give it the whole code base? Why might this be? And what might a fix be? All right. Oh, sorry. Santos, how do you even make an OS? Like what are the basics? Is there a GUI? No GUI, unfortunately. The way you make an OS, the way that I'm doing it is I just used this MIT course that's on the internet. I will link it here, and if you want to follow along. And they like give you like an OS that like kind of works, but it kind of doesn't. Is this C++? No, this is C right now. To copy data. Okay. So here it is. I mean, yeah, that's good to know. You're not allowed to use SSE or MMX or whatever instructions until the CPU has enabled them. Yeah. It's doing something like weird. Yeah, something like that. I'm gonna guess it's something to do with the number of arguments that are passed here. This is a little bit unusually high number of arguments for the kernel, generally speaking. So I don't know, maybe that made it exceed some threshold where Clang thinks it can be super smart. I mean, one other option is there are quite a few flags available. Like specific CPU and FPU and blah, blah, blah flags. We could consider using some of these because without passing these, I think it just chooses some default. And we're not really prepared to handle very advanced hardware. So yeah. Okay, so what was the suggestion? No SSE, no blah, 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 blah. Yeah, no, I don't really feel like using that. I mean, also, yeah, another reason why that possibly happened is because we actually do enable optimizations in the C flags. We're using O1 optimizations. And the reason for that is because that's how it was by default. This comment explains it. And also, anytime I tried to disable that, like the kernel would not boot anymore. And I never debugged why. So we actually are enabling O1 optimization level, which might be the cause of this. Anant, can you change architecture x86-64? So right now the kernel only runs, well, it's only designed for 32-bit, and it's not tested at all whether it works on a 64-bit emulator. Yeah. Although I would say that is in the roadmap. Okay, so easiest fix would be something like this. It's kind of interesting that, hello? Okay. Clang from emitting SIMD instructions. That's kind of interesting, actually. Okay. Okay, let's get out of here. Okay. Let's rebuild. Let's run it. Kimu. Yo, check that out. That's cool. It's running. Clang built kernel is running. Try to use a 16-byte register on a 20-byte parameter size. Yeah, that's weird. That's It's weird, but whatever. Check this out. At least initially, it does seem to be working. We can, I can cat index.html, and we can run some processes. Yeah. I don't know. I kind of forgot what these things even do. We can run the primes program and start calculating some primes. Although I think can I even stop that though? Yeah, I don't know when it does primes calculation with this weird thing where it makes a new process for every prime or something weird like that. So I also don't think I can even get out of that. So I need to quit the system. But check that out. That is cool. So that was relatively okay. It was an interesting debugging adventure to see these SIMD instructions in use. And I guess the lesson here is like that's just part of the general like surface area that the compiler has to use. And even if you're using standard C, stuff like which instructions the compiler is using is not part of that guarantee. And since we're making an operating system, we're sort of exposed to this in a way that normal developers wouldn't usually be exposed to. Like it normally wouldn't be a problem if you switch your code base to Clang that it uses SSC, because usually you're running within an operating system that has already set that up. But we can't handle that, and we just crash. So that's kind of interesting. So basically that was kind of it. Prevent use of SIMD instructions. Yeah, thanks Anant, thanks Ismail, thanks Useless. Nice. So that's pretty cool. So now we're able to use Clang, and yeah, I don't know. It doesn't really matter too much right now, but when we start using more C++, it could be helpful. And yeah, in general, it's just a more modern compiler infrastructure. Maybe it even allows us to do interesting things with address sanitizer later on. Or, I mean, since we can compile the kernel with Clang, we can compile it to Clang intermediate representation and run some analyses, passes on that or whatever. So yeah, Clang tooling is way better. Just trying to think if there's anything else worth trying or mentioning. But I don't think so. I think that was, we just quickly review what it took. So commit number 1, all we need to do, switch out GCC with clang-target blah, blah, blah. And turns out my Clang already had a cross compiler built into it. We needed to do a little bit of stuff to make sure we kept using the same libgcc. And then there were just a bunch of these miscellaneous warnings that we needed to either fix in the code, like right here, or simply hard disable the warnings. And then lastly, prevent use of SIMD instructions. And then so we're not done, but that brings us to, I don't know where my pen tool went, but like that brings us to this checkpoint. my pen tool. Yeah, address sanitizer. So it's not going to work out of the box, but I think it is possible. I mean, Linux has this. Linux has kernel address sanitizer, and I'm not sure if that's only possible with a Clang built Linux kernel, but from what I understand, it is possible to use that technology with kernel, but it's just harder. You just need to, like, usually as a application developer, you just turn it on and it just works for your program. But if you're using it for a kernel, you actually will need to do some integration work and like implement some functions that the compiler runtime will need to call. In the same way as with the libgcc thing, except we will just need to implement our own version of like the lib. It's like a lib asan or something like that. Okay, so we made a nice first attempt. We got this working, and then next up would be get rid of libgc. GNU libgcc, try to use clangs, like lib clang. Next step, and then the next step would be stop using GNU linker, assembler, etc. Use LVM ones. I don't know. I don't really know. Yeah, that's like a little bit tricky. Like, it's one thing to have a cross compiler, but I would be pretty surprised if my system also has like the linker also works with x86 and stuff. So yeah, that's the vision. All right, I think that's gonna be it for today, everyone. Also, quick question from Chi Kung Fu on Twitch. If you have time to answer, as you learn programming, how did you handle the forest of header files? Forest of header files. How did you handle? I think I didn't learn about headers for a very long time. Like, for the longest time, I was just playing around with my own little C programs where I didn't even have headers. And I only really started to learn about headers once I started working like professionally with a larger C++ code base, where we actually had a lot of files and headers and stuff. I'm not like totally sure what your question actually is, but feel free to join the Discord, and I'm happy to chat about that later. But as usual, I will just self-promote myself. Feel free to join the Discord if you want to keep chatting about stuff. And subscribe to my channel. Yeah, subscribe if you dig this stuff. Twitch channel name is the same name as Offline Mark. If you feel free to join there too if you want. Yeah, I think that's gonna be it. Have a great week, and I'll see you next week for a bit more of trying to get rid of GNU libgcc. All right, peace. See you.